Alright, so this is what we had seen, the CMOS latch in the last lecture, where we had this particular inverter. So this particular inverter is used to make sure that the input noise doesn't get passed into the output of the flip-flop. And this particular inverter is there so that we avoid the sensitivity of the output noise getting coupled into the input of the latch design. This particular the tri-state inverter, which is there in the feedback, is there to make sure that this particular X node is staticized and it is not dynamic anymore. So if it remains to be dynamic, or if it remains to be floating, there is a possibility of the X node getting discharged to a lower voltage, or getting charged to a higher voltage. Thereby, this particular output or the X node voltage level will change due to the subthreshold leakage current. And for the same reason, what we have done is added the tri-state inverter, especially when the latch is in the opaque mode, or when it operates in the 5-bar mode. That is when the clock is for the low level of the clock. That is when we so this particular tri-state inverter is ensuring that the X node retains to the previous X node, right? Doesn't get any changes in the voltage level, and doesn't have any any change in the output values of the latch, right? So this is the most recommended latch and used in the standard cell library, including the artisan cell library. Let's take a look at another latch. It is called as Jamb latch. So instead of the tri-state inverter, here we are using a weak inverter, right? And everything else remains the same. We have the inverter at the input side, we have the inverter at the output side. So it takes care of the it takes care of being an insensitive to the input as well as the output noise. So this one replaces the tri-state inverter in the feedback part with a weak inverter. The advantage of the weak inverter is the weak inverter is of 2 transistors. The inverter is naturally of 2 transistors, whereas a tri-state inverter, because it is a clocked, the 2 transistors, the input of the 2 transistors are being clocked. So we have 4 transistors in a tri-state inverter, whereas in the weak inverter we have only two of the transistors. So it saves 2 transistors in the feedback path. The other thing is, the clock in the tri-state inverter. So let me draw the tri-state inverter here. So if I go back to the previous slide, so this is what I'm talking about, the inverter, tri-state inverter, which is kind of clocked. So what we had was a tri-state inverter, right? And so this was considered 5-bar, and then this one was 5. Right? So what it means is I have now 4 transistors. Okay, of course this one will be the VDD rail, and then this will be the ground rail, and then this being the PMOS, this being the NMOS, and we have this connected to the this one, and then this one is 5-bar. Notice that this is 5-bar, so that is when the clock level is low, these 2 transistors should be on. So this should be 5-bar and this should be 5. And the input here is nothing but this coming from here, which will be nothing but Q, right? So this particular output is what I am considering here, Q and Q, right? Remember, notice that these 2 transistors, whatever is the width of these 2 transistors, if it would be regular size of 4, 4 and 2 and 2. So this goes to the clock. This clock is also driving this particular transmission gate, right? So if I draw the transmission gate here, somewhere here, so I'm drawing this particular portion, and the transmission gate here, so I will have the 5-bar here, I will have the 5 here, right? What it means is these 2 connections, this point and this point, are actually connected, right? And then this 5-bar, this one and then this one are also connected, right? And what it really means is, if there is a clock that has been generated, so the clock circuit is there, and that is generating the clock signal. So there is a circuit here, which is generating the clock signal. So it is giving the clock signals. It not only has to drive this particular transistor, it has to drive this particular transistor also, right? And similarly, this inverted one will go to drive this particular transistor and then this particular transistor, right? So based on this particular size of the transistors, this clock or whatever the generating circuit, it needs to drive for the total capacitance which is there here as well as here, right? Based on the width of this, it will have an effective total input gate capacitance which it needs to drive. Now, any kind of an additional load is going to make this clock generating circuit or any kind of a circuit to be really slow. So we need to increase the strength of this particular clock generating circuit, right? Whereas in a weak inverter, I don't have this clock connection to the transistor, right? We have in a weak inverter, it will be nothing but two of the transistors, and then that's about it. So this will be the weak inverter. So it's an inverter design basically. So there is no clocked transistors. So that's the reason it says that it reduces the clock load. So the additional input capacitance will act as a load to this clock generating circuit, right? So this will be my clock generating circuit. So additional transistors here in the feedback path, which is nothing but the clocked or the tri-state inverter, is going to add to the input capacitance of this particular clock generating circuit's output. So that is getting reduced with the help of this weak inverter. However, there is a contention current during the transparent mode of the latch, right? Transparent mode of the latch is when this particular transmission gate is going to pass, and because this is a weak inverter and doesn't have any clock to control it, this is going to be operating every time. So it is going to pass a signal, output signal every time. And this transmission gate, this is going to be passed due because my clock is high and that is in the transparent mode. So there will be a signal here, there will be a signal here. So X will be in contention. So let's have a look at it in more details. So what I mean. So I have this inverter. All right. So this particular inverter, I'm going to, in fact, let's draw everything in let me see. Yeah, let's draw everything in the transistor level. So we have an inverter first. Right, so this is the inverter. This goes to the transmission gate. So the transmission gate, this is phi and then this is phi bar. Right, and then this goes to one more inverter. So let me draw a gate level diagram, and here I'm going to draw the the transistor level diagram, and this is a weak inverter. So I'm going to draw an inverter first and then talk about being weak. So this will be the inverter, and finally it gets connected to the node X. All right, so this is my node X, and then it goes to the the other inverter and so on. Right, so this will be my Q signal, right? Right. So in this sense, this is the input here. Let's say the input is 0, right? In a transparent mode, that means when the clock is 1, so clock bar will be 0. So both this PMOS and NMOS will be on, and then if it is 0 here, this will be 1 here at the output of the inverter, and it is going to drive the transmission gate. So the current that will be there, and then I'll also draw this particular capacitance here. Some particular capacitances will be there. So CX is going to get charged through this particular VDD rail, because this is passing, these two transistors are passing, and the VDD is going to charge the CX node here. Right, so whatever is the capacitance at the X node is going to get charged from this particular VDD rail, because D is equal to 0. So that means that this will be on and this will be off. And then this on transistor, the PMOS on transistor, as well as this particular, both the transmission gates transistors, both the transistors, because the clock is 1, transparent mode, both of them will be on. and so the CX node is going to get charged from this particular VDD ring. Let's say that previously Q was 1. So if it is 1, it will pass 1 and then 0. So previously, let's say it is 1. So this means that it is going to change from 1 to 0 because of this 0 and then 1 and then this particular value will be 1 and then finally it will be 0. But let's say that the previous state it was 1, right? Because it was previously 1, and now when the clock from 5 to 1, so during this particular initial portion of 1 of the clock, that is when the D is equal to 0 here, right? So the previous state of the Q is 1 here, so that means that this particular NMOS transistor is on. So CX mode was completely, because this is 1, this was held to be 0. That means it was held to be 0 means this particular mode is on, right? So because this NMOS is on here previously, so the NMOS is driving the X node to the ground, whereas because D is equal to 0 now and this one will be 1, that means that this PMOS transistor from here is going to charge the X node to high, whereas this particular transistor is going to make the X node discharge to ground, right? So the X node here has a contention. That means that there is one particular path, charging path, and there is another discharging path. So that's the contention we are talking about. And to avoid the contention, whichever current is lower, that is going to lose. So that means that whichever current is dominant, that is going to win, and ultimately X is going to favor the dominant current. And we can do that by sizing this particular transistors more. Let's say if I have a size of 10 here, if I have a size of 10 here, and if I have a size of 10 here, right? And whereas here, if I make the size of 1 and 1 here, right, the width of this particular transistor is actually very, very less than that of the size of the transistors here. So the current that will be passing for charging the X node is actually more, right? It is actually 10 times more than that of the current that is passing that is actually used for discharging the X node, right? So that's why I make this inverter as a weak inverter, which will help in finally making the X node, right, pass the input here, right? If it is 0, it is 1, and then this one will be passed here. So in the transparent mode, we want this particular path to win over the feedback path, right? So if I am using a weak inverter here, and make weak inverter means the width of this particular tri-state inverter to be less, so that the forward path, not the feedback path, the forward path is going to likely to win during the transparent mode. And in the opaque mode, this path is anyways off because the clock will be 0. So this particular transmission gate will be off. This particular transmission gate will transistors will be off. So the transmission gate itself will be off. So there's no forward path. The only path is the weak inverter, which is nothing but the feedback path. Right? Hope this is clear. Moving ahead. This is one more variant of the CMOS latch. Instead of the weak inverter or instead of the tri-state inverter, it is basically a combination of both. So this design is basically between the 7 and 8. So here, if you notice that the pull up part is taken from the weak inverter and the pull down part is taken from the tri-state inverter, right? If you notice the tri-state inverter, let me redraw that, the tri-state inverter. So I'm drawing the tri-state inverter in the feedback path, and just placing the transistors in a different way. Yeah. So let me complete this diagram. Right. So this is my VDD, and then this is my ground. So this is the PMOS, this is the PMOS, this is the NMOS, and then this is the NMOS. So notice that in the tri-state inverter, when in the feedback path, if I had a tri-state inverter or the design number 7, which we said that was the most recommended one. So this one was coming from the output Q or whatever, the output Q bar in this case. And this too was coming from the clock. So we said that this is 5 bar and then this is 5 because when the latch is in opaque mode, that is when the clock bar that is will be fed to the NMOS and then clock will be fed to the PMOS, right? So what we had done is in this particular design, the 9th design, this particular portion of the pull down side is taken, and for the pull up side it is nothing but the pull up of the weak inverter. So it is kind of the pull up side, it's nothing but a normal PMOS transistor, but it's a weak PMOS transistor, right? So that's what is written here, the weak PMOS transistor, and the pull down side is taken from the tri-state inverter. So the advantage is instead of the 4 transistors, or we have 3 transistors, and the other advantages, the other advantages with respect to the weak inverter is on the pull down side, it is not weak anymore. So, and there won't be any contention. The moment the contention is there, there will be more delay to pull up or pull down the X node, so based on the input. So because there is no contention on the pull down side, because it is now clocked properly, right? So during the forward path, if at all the X has to go down, or rather go up here, the X has to go up here. So it will, this particular path, this particular pull down circuit is not going to pull down the X node, right? It will easily go to the pull, it will easily go to a VDD level, right? So in that sense, it has disadvantages, or rather it has advantages. So at the input side, inverter is not present and sensitivity to the input noise. So this particular portion, we always had an inverter in the last 2 designs. So that is taken away. So if that is gone away, then we will have its input noise sensitivity issues, and that's what is this particular latch is having, because the inverter is not there, but the output inverter is there, so it becomes insensitive to the output noise, which is a good for the circuit, right? So that's about this particular circuit 9, right, or the design number 9. So we saw design number 7, we saw design number 8, and then design number 9. So let's take a look at the tri-state inverter before going into the flip-flop designs. So the tri-state is kind of symbolized in this particular way, and its transistor level schematic is shown here, where the D input is going to the D input, or the Q input is going to the transistors closer to the VDD and ground rail. And we have the clock given to the transistors which are closer to the output node. And let's draw a set of parasitic capacitances here, just to notice what really happens. So C1, C2, and C3 are nothing but the diffusion or the merged or unmerged diffusion capacitances, right? So let's say that when phi is equal to 0, that is in the latch is opaque, it's not in a transparent mode. That is when so this one will be working. So what happens if the phi is equal to 0 in this particular case? If phi is equal to 0, this one will be off, and then this one will be off. So when the phi is equal to 0, that means phi 1 is equal to 1, so the PMOS will be off. And let's say that the input changes, right? So if the input changes here, so what we really don't want is, if this is off or the phi is 0, that means the output node should not change at all, right? But because these 2 clocks are 0 and this will be 1, so these 2 transistors will be off. And if D changes from D changes to 1 here, so that means that D will be 1, so that will give us, this one represents that this will be off, and then this one will represent this will be on. So now I have the C3 can get completely discharged to the ground, but the C2, because this is an off transistor, the C2 which is connected to the output node doesn't drop at all, right? Because this is not at all, Y node is not at all connected to the C3 node, right? And then similarly, if I make D is equal to 0 here, this will become turned on, the PMOS transistor, and C1 will get completely charged to VDD. but output node is not getting disturbed because this particular clock has ensured that the PMOS transistor is off. So the output doesn't get disturbed at all in this particular case, and that's why it is a very good design. So normally the clocks in a tri-state inverter, the clocks are given to the transistors. So clocks in the sense clock and clock bar are provided or fed to the transistors which are closer to the output node. The input is given to the transistors which are closer to the VDD and ground rail. So if I actually take a different design where the clocks are connected to the transistors closer to the rail, VDD and ground rail, and an input is given to the transistors closer to the output node. So the input are given to the inner transistors, so output are given to the outermost transistors. The clocks are fed to the outermost transistors. So in that case, what really happens? If phi is equal to 0, that means it's in the it's in the opaque mode. So phi is equal to 0 represents. So this is off, and phi bar will be 1, which will be nothing but this will be off. Right now, if D is equal to 1 here, D is equal to 1 here, so that means that this will be on, and of course this will be off here. But this on transistor will ensure that whatever is a node voltage, initially let's say it is connected to VDD. Now the charge from C2 will be shared to the C3 capacitance. Although this transistor is off, but C3 is kind of connected to the C2 capacitance via this particular on transistor, and thereby the C2 and C3 are going to share the charge, and thereby the output node voltage level is going to get dropped, right? So in this sense, the output level is kind of disturbed. The other problem is if D is equal to 0 here, D is equal to 0 represents this will turn on. Right, so if this is made 0, so this will be on, and then this will be off. So this on transistor is now making C2 and C1 kind of connected by the transistor. And if it was C2 was C2 was VDD at VDD level, then it is going to charge to C1, or if it was at 0 voltage level and C1 had some particular amount of voltage across it, then this C1 is going to share the charge to the C2, and thereby the output node voltage is likely to change. So the charge of C2 is going to be shared by C1 now, and that's why the output is disturbed. So this is a very bad latch design, or rather the tri-state inverter, that if at all we were to use it in the CMOS latch in the feedback path, this design becomes a very bad contribution to the design. So normally when we design a latch, or when we use a tri-state inverter into the feedback path of the latch, the clocks are provided to the innermost transistors, that is the transistors closer to the output node, and the inputs are given to the transistors which are closer to the rail voltages. Right, hope this is clear. Moving ahead, let's introduce to the CMOS flip-flop. As we know, flip-flop is made up of two latches, L1 and L2. Right, so if I have a clock here of a high level and then followed by a low level of clock, then this behaves like the flip-flop. So the input, whatever is the input that is being provided, so let me draw the simple timing diagram. So if this is the clock here, and so let me take the input somewhere here. Right, so if let's say this is the input here, so D is my input for the first latch L1. So this D is going to pass as the output of the latch, latch L1 during the high level of the clock. So during this particular level of the clock, whatever is the D here will get passed, right, at the output of the latch 1, and it has to wait for the latch 2 to become active, and the latch 2 will become active only during the negative level of the clock. So whatever it has passed from 0 to 1, in this case 1 will be, it has to wait till it the negative level of the clock has reached, because that is when the L2 is going to pass the signal from the input to the output, right? So the input to the output is passed from positive level to the negative level. So that is during this particular transition of the positive to the negative level, that is when the input from here, this portion of the input of the first latch will be passed to the input to the output of the second latch, right? So this works like a flip-flop, because flip-flop is operating only on the clock edges, right? So to just use the latch design and then derive the flip-flop design, it is very simple. So we use the very basic CMOS latch design, where we have the inverter here and an inverter here, inverter here and inverter here. And the outputs of the latch design helps in making the circuit more insensitive to the input and output noise. And we have the transmission gates here, which is going to pass the input to the output based on the clock level. So this clock level is high, that is when it is passing the D to this particular portion. And we have another transmission gate which is operating at 5 bar, so that is when the clock level is low. So this particular input to this particular second latch will be passed to the output of this particular transmission gate, right? Again, this design has problems. So the X is not satisfied, so there is a possibility of the X getting discharged due to the subthreshold leakage current. So it is not satisfied, so that means that it is in dynamic mode, it's in a dynamic state, or it's in a floating node voltage, so it can drop due to the subthreshold leakage current. And this works like a negative edge flip-flop, because negative edge means the decreasing edge or the falling edge of the clock, we can say that. And it's negative edge because it is it gives the output at the negative edge of the clock. That is when the transition is falling from the clock from high to low. That is when it is going to give the output, and that's why it is called as a negative edge flip-flop. Right, just to make it more robust design, just as we had done for the CMOS latch, we are introducing the feedback path, or the tri-state inverter in the feedback path, to ensure that this particular node and then the X node here, as well as the X dash node here, is staticized, right? So very similar to the latch design, what we are doing is we are bringing in the tri-state inverter here to ensure that this X node, although there will be a subthreshold leakage current, the moment it drops a little bit, there will be a charging back from this tri-state inverter, or if it is getting charged due to the subthreshold leakage current, it will ensure that this has a stronger discharging path connected to the ground. So similarly on the X node also, so X is now staticized, and then of course there is the inverter at the input side and then the inverter at the output side, making sure that the Q bar is isolated from X, so whatever is the output noise here doesn't get coupled into the X, and whatever is the noise at the input side doesn't get coupled into this particular path. So a Q bar is isolated from X, and of course it is a negative edge because I have this this latch design is working as a transparent mode when the clock is high, and this particular transmission gate this particular latch design works when the clock is low. And that's why it is said that this is a latch of positive clock and this is the latch of a negative clock, and thereby it works like a negative edge flip-flop. Notice that this tri-state inverters, as we have seen in the CMOS latch design, the tri-state inverter here, if it gets clocked, this clock of the tri-state inverter has to be opposite to that of the transmission gate. So for this particular latch, we know that the clock is 5, so the tri-state inverter should work in the 5 bar mode, that is in the opaque mode, and transparent mode, this particular transmission gate will pass the signal in the lower level of the clock. This particular feedback path is going to pass the signal. Whereas for this particular latch, it is working in the 5 bar mode, so the tri-state inverter here should work in the 5 clock, the positive level of the clock, and because this particular latch is transparent during the low level of the clock, and then thereby the feedback mode or the feedback path should work in the positive level of the clock, right? So that's the additions which we have done in this particular CMOS flip-flop design.